Okay, so this morning we're going to tackle the problem of a frame, and in this case, a frame which, on its first look, seems to have more reactions than it has equations of static equilibrium. Now, the specific of this particular frame is that it introduces a hinge, and that hinge, shown here at the apex, is going to allow us to use the method of sections and break it out and to solve for our reactions effectively by providing a condition that gives us an extra equation, if you will, to solve for all of the reactions. So once we solve for all the reactions, we're going to go through, we're going to track what the forces are, internal forces throughout the frame in all of the members. We're going to look at them in context of global coordinates. And for those that are where the members don't align with the global coordinates, we'll look at what those forces are in accordance with their local coordinates so that we can draw the shear force and bending moment diagrams for each of the members through the frame. So we're going to get right at it. We're going to start. We've drawn out the frame in small so that I can draw the free body diagram. And so I'm going to start by adding the reactions to that. And of course, we have reaction at A in the X and the reaction at A in the Y. And we get the same at E. So reaction EX and reaction EY. Of course, we have to add our externally applied loads. So we have our uniformly distributed load of 5 kilonewtons per meter on member AB. And we have the point load of 15 kilonewtons applied at the joint at D. And with that, we have our free body diagram. Now, if we look at what we do have for statics, we're not stymied right away. So using statics, we can solve for one of the reactions if we choose a good point to do the sum of the moments about. So in this case, if I choose to do sum of the moments about A, and I will use clockwise positive, and we set that equal to 0, if we walk through this, we see that that's equal to the 5 kilonewtons per meter times its length over which it's applied times its moment arm. So its perpendicular distance from A is 2.5 meters, or halfway up AB. And the 15 kilonewtons also turns it clockwise. So we have 15 kilonewtons, and its perpendicular distance is, of course, the distance between A and E. And so we can put that in as 8 meters. And the reaction EY tries to turn it counterclockwise. We'll put it in as negative reaction EY, and it also has a perpendicular distance to it of 8 meters. You'll note that the reaction E at X passes through the point A, and so it has a perpendicular distance of 0, and so it doesn't come into play. And so we're able to look at this and solve that. So reaction EY is equal to 22.81 kilonewtons. And draw that in there. So we can do one more. We can go on and look at the sum of the forces in the y direction equal to 0. We'll use for this positive up. And so we have RAY minus 15 kilonewtons for the point load plus REY, which we know is equal to 22.81 kilonewtons because we've already solved for it. and we can resolve RAY and determine that it is equal to negative 7.81 kilonewtons. Of course, the negative sign simply means that it's going in a direction opposite to the way we've drawn it, and we can fix that at any point in time. So let's add that to our diagram. RAY is equal to negative 7.81 kilonewtons. So at that point in time, we're kind of stuck. Some of the forces in the x direction isn't going to be sufficient for us to resolve RAX and REX. We are short an equation, and so we're going to have to take advantage of that hinge that we talked about earlier to resolve the next set. So basically what I want to do is we're going to isolate the left side of the hinge at C. And the reason why we're doing that, recall that because it's a hinge, it can't transfer a moment through that joint, so the moment at C must be equal to 0. And that's the trick that we're going to use to be able to resolve that. So I'm just going to bring up my half section. Okay, I've pasted in my half section, so it's a free body diagram, so we're going to have to draw in what we know and don't know on it. So the first thing I can do is put in my reactions again at A. So we have reaction AX. We have RAY. Of course, in this case, we know it's going down, so I may as well draw it going down as RAY equal to 7.81 kilonewtons. I'll put in my uniformly distributed load like we did before. Of 5 kilonewtons per meter. And then I need to put in my internal forces. At C, we know there is no moment. However, there quite reasonably is a C at X and a C at Y. And we don't know what direction they're going in. We'll just draw them that way. And note that I choose to draw those in the global coordinate system. The global coordinate system may as well indicate here. We've assumed it, but we'll do X and Y. And wherever possible, I'm going to stay in that global coordinate system because it's going to simplify my process. And I'm only going to deviate from it when I have to later to draw the shear force and bending moment diagrams. So with this drawn out, we actually do have what we need to resolve the next thing. So let's go back to statics once again. And what I'm going to do is do the sum of the moments about C, or about the hinge. And so we'll go sum of the moments about C, always equal to 0. Again, I will use clockwise positive. And so if I'm looking at this, so RAY is trying to turn it counterclockwise. So R negative RAY, and its distance between C, perpendicular distance between C and RAY is 4 meters, minus RAX is a negative because it's trying to turn it counterclockwise, times 8 meters, minus the 5 kilonewtons per meter times 5 meters, and its perpendicular distance is the distance down from C to point B, and then another 2.5 meters. So that's 3 plus 2.5 is 5.5 meters. And you'll see that we already have, well, I should have written it in there earlier, so this is equal to 7.81. So we already have that value. So this whole equation has a single unknown, which is RAX. So we can solve for RAX equal to negative 21.09 kilonewtons. And again, the negative sign just simply means that RAX is actually going the other direction from the one we drew. So that's equal to negative 21.09 kilonewtons. So we only have one reaction left to resolve, that's REX. We haven't applied some of the forces in the X direction for our whole system. So we're going to do that. Yes, return to full frame. So not looking at the frame to my left here, but looking at the one above that, looking at the full frame. So sum of the forces in the X direction equals 0, and that's equal to RAX, which we know is negative 21.09 kilonewtons plus 5 kilonewtons per meter applied over the 5 meters of length plus REX. And so we have a single unknown REX, which we now can determine to be equal to negative 3.91 kilonewtons. And I'll go ahead and mark that on our diagram. 3 equals negative 3.91 kilonewtons. So that's it. So we've gone through the first part by taking advantage of that hinge and doing the sum of the moments about the hinge on a partial frame using the method of sections, knowing that the moment would be equal to 0. At that point, then we were able to resolve the extra unknown. And so we have all of our reactions determined. Now all we have to do is pedantically move through the frame in a way that's going to allow us to calculate what the internal forces are at each of the ends of the frame, if you will, and pass through the joints and get onto the other side. So I'm going to reset my page. I'm going to draw out my diagram in a fairly large exploded format so that I can work my way, left to right, right to left. You can go both directions, either direction or both directions, and we're going to get that. So let's reset the page. Okay, so I have my page reset. I've got the frame blown out, showing each of the members and the various joints. I've labeled it. I've drawn on all of the reactions, and I've chosen to put them all in a positive sense, so they're pointing in the direction that they are actually going. And I've labeled this diagram to be very specifically global coordinates. I am not going to worry at this stage at all about the members that are off angle or anything else. We can deal with that later. So you can work left to right, you can work right to left, it doesn't really matter. What we're going to do is to apply the equations of static equilibrium on each of the members. Now, this is kind of a pedantic, slow-moving process. Quite frankly, I do a lot of the calculations mentally, and there really is only calculations to be done at the ends with the sum of the moments, or if there's a force applied at the member of the joint, which needs to be added in. So the first one, I'll just walk through this. We're talking internal forces. So if we have at A, we're looking at the member AB. If we have 7.81 kilonewtons pulling down, we know from a static equilibrium perspective, we must have 7.81 kilonewtons pushing up. Just like if we have 21.09 kilonewtons pushing left, we have to look at the difference to that. So the 5 kilonewton per meter applied over the length of 5 meters is 25 kilonewtons. So the 25 kilonewtons pushing to the right, 21.09 pushing to the left. We need an additional 3.91 kilonewtons going to the left. Now, there's also the potential that there's a moment there, and so that's the one calculation I tend to do out in writing, because otherwise I can found that I can sometimes mess up my sign. So I'm going to do the sum of the moments about B equal to 0. I'll use my clockwise positive, and that is going to be equal to our reaction at A in the X, which is 21.09, which we'll try to rotate it clockwise, multiplied by its moment arm of 5 meters. I'm going to run out of space, so I'm going to leave the units out of there. And we know that the 5 kilonewtons per meter over 5 meters is 25 kilonewtons, and it's going counterclockwise, so the negative sign multiplied by its distance to the centroid of 2.5 meters, and to all of that we would have to add the moment at B. Resolve that for moment at B is equal to negative, where's my sheet here? 42.95 kilonewton. 0.95 kilonewton meters. The negative sign just means it's going counterclockwise. So we can draw that in this way, and 42.95. And then we can transfer those to the joint. And of course, when we do that, they're equal and opposite, so we're going to have to flip the signs. So I'm just going to very quickly go here, and that's your 3.91. Go down at the 7.81, and a moment going this way of 42.95, and there's no forces applied, so we can just very quickly carry on. Again, 3.91, 7.81, and our moment of 42.95. And from that joint, then, we're going to apply them to the left end over here. So we have our moment of 42.95. We have our horizontal force of 3.91 going to the right. And we have our vertical force of 7.81 going down. So when we go to the right end of BC, the vertical and the horizontal component, they're fairly straightforward because there's no forces applied. So we can do that. And we get our 3.91 to the left. The 7.81 is down. So this has to be up to get equilibrium, 7.81. However, we need to calculate our moments to check to see what is going on. So again, I'll do that out by hand. I kind of already know what I'm hoping turns out, otherwise I've got myself a mistake. So I'm just going to do sum of the moments about C is equal to 0, working left to right. So the moment at the left side is 42.95, trying to go clockwise, so positive, so 42.95. Both the horizontal and the vertical components try to turn it counterclockwise, so we'll subtract those. So 3.91 times its perpendicular distance of 4. Oh, sorry, its perpendicular distance of 3 minus 7.81, its perpendicular distance of 4. And of course, to all that, we're having our moment at C. And as we had hoped, when we run that out, we end up with no moment at C, which we know has to be true because of the hinge. That's what allowed us to solve this out in the first place. So far so good. Again, you can be working right to left and left to right all at the same time, different directions. It will all come to balance. So let's carry on at joint C, and we'll move our forces. So we have our 7.81 and our 3.91, which equal and opposite here. And of course, there's no dimension in the joint, so there's no moments created. 3.91, 7.81, which also means we have no moment at C there. And 3.91, 7.81. And then we're going to have to calculate our moments at D. So again, I tend to do these out in longhand, otherwise I make a mistake in the errors. So let's try that. Sum of the moments at D is equal to 0, clockwise positive. So that would be our moment at D. Actually, let's work left to right. So we have no moment at C. So we have 7.81 times our perpendicular distance 4. That's going counterclockwise. So that's a negative. 3.91 is going the other way, so it's a positive 3.91 times 3. And all of that has to be to get our moment at D, which allows us to resolve for our moment at D, which is equal to 19.55. And that's a negative sign, negative 19.55. So we can add that onto our diagram. Which means that that transfers there, 19.55, and do our 3.91, our 7.81. So 19.55, and our 3.91 is easy enough. We have that going to the left. However, our vertical one, we now have to add in the 15 kilonewtons. So we have 7.81 going down, 15 kilonewtons going down. So we have to resist both of those. And so we end up with a vertical internal force of 22.81. Transfer those down to our member DE. So this is equal and opposite going down, 22.81. And, 3.91. And our moment going this way of 19.55. So you can see your DE if you look at the reactions at the bottom. Certainly in the X direction and the Y direction are canceling out. If you do the sum of the moments equal to 0 about either D or E, you will find that they cancel out as well and that there's no moment at E, which gives us some satisfaction or some confidence that we've gone through this correctly without introducing any minor errors. So that's the big step. So we now actually know what the forces are, the internal forces are in each of our members, left side, right side, but in the global coordinates. Certainly when it comes to the two slanted members, if we want to draw a shear force diagram and bending moment diagrams, we're going to want to know those in terms of normal forces and shear forces, or orthogonal to the cross section and parallel to the cross section. And so we're going to have to, for those two members, BC and CD, we're going to have to convert those to local coordinates. So let's do that over to the side before we move on. Choose here. So local coordinates, and we only have to worry about those two members. The other ones, global coordinates and local coordinates, align. So we don't have any calculations to do in those cases. So local coordinates, and I'll draw these out fairly large. We only have to do them on one side because they would be reflected on both sides. So this is going to be BC. And just to be aware, I'll just mark it up here at the one end. Keep in mind that this is a 3, 4, 5 triangle. You can also use your thetas and derive that down to an angle and cosines and sines, but we can use those ratios of the triangle. So what I need to do is I'm just going to work from my end at B, and I'm going to draw in my forces. And so the first one I'm going to draw in is my 7.81 vertical force. So my 7.81 vertical force we know is coming down. And we want to break it up into its components, normal and parallel to the cross section. So if we draw one of those components there, the other component will be here. I'll just draw those in here. So this is 7.81. And I'm going to call that V prime and that one N prime. You have to make sure you get your arrows going in the right direction because they're going to add to each other or subtract from each other depending on what they do. Now, before I leave it, I'm going to go ahead and draw in my 3.91, which is going to the right. So I'm going to draw that. I'm just going to, and I'm not worried about scale here. I'd rather you be able to see what we're doing. So that's 3.91. And again, I'm going to have to get an orthogonal component and the one that lines up and get our directions, our arrow directions. So that's going this way and that way. And I'm going to call that N double prime and this one V double prime. So really all we have to do is to take those two forces in their global coordinates, use the ratio of the 3, 4, 5 triangle to determine what V prime, N prime, V double prime, N double prime are, and then combine them in accordance with their direction or sense, and we will be able to determine what V and N are, which are the forces in the local coordinates with respect to BC. So really, I'm going to resolve them here. So N prime is equal to, and if you look at N prime, so that they are all in relation to this 3, 4, 5 triangle. So the 7.81 is the hypotenuse, the N prime is the shorter of the two sides. So that means that this is 3/5 of 7.81 or 4.69. And if I look at V prime, that's going to be the longer of the two sides relative to the hypotenuse, or 4/5 of 7.81, or 6.15. And then I'll resolve the 3.91, so that will give us values for N double prime. It is on the long component of the hypotenuse 3.91, so that's equal to 4/5 of 3.91. 3.13, and then V double prime is equal to 3/5 of 3.91 or 2.35. Now, I haven't given these any signs. We have to draw our direction or sense from the diagrams themselves, and so that means that the shear force at B in the local coordinates would be equal to V prime plus V double prime, because they're both going in the same direction. V prime plus V double prime, and that's going to be equal to 8.6 kilonewtons, of course, and that's down and to the right. So, and I'll just put it as down because that's down in the local coordinate system. And n at B is equal to n prime plus n double prime. And if I look at the signs, so n prime is reduced from n prime. So I'll put in it as negative, meaning that if we get a positive answer, it's going to be going to the right. And if we sum those up, we get a value of negative 1.56, which means it's actually going to the left. And so I'll note that as left. I'm going to get rid of my negative sign by noting that it is to the left and or tension, if you will. So really we just have to repeat that process for the member CD. So let's get on about that. So we've drawn out member CD, and I'm going to add our forces to it. Again, I'm going to use, just so you can discern them, two different colors. So we have 7.81 acting down. I'm looking at the left-hand side, so that's 7.81. And when I resolve that into its perpendicular, so we have these two components. And to add up to that, they need arrows in those directions. And our 3.91 is acting to the right. 3.91, and it will need components. Here, notice that these are always drawn at right angles to the member. And I'm going to go ahead and label these. So the green in the first case, so this is going to be n prime. That will be, v prime. And draw the arrows in here. So that's going to be n double prime and v double prime there. So now all I have to do is resolve those. Again, using the 3, 4, 5 triangle, I'm just repeating the process that we used earlier. So n prime is the smaller of the ratios, or 3/5 of 7.81, 4.69, and v prime is equal to, then the higher the ratio is, 4/5 of 7.81, 6.25, sorry, I'll have to check, my numbers should carry through, 6.25, and n double prime, looking at in blue, or the 3.91, the n is the longer, or the 4/5 of that ratio, 3.91, 3.13, and v double prime, that is the 3/5 of 3.91, and that's equal to 2.35. So in combining them, then we have our v at C is equal to our v prime in the opposite direction is v double prime. So that's equal to 3.90 down. And our normal force, our normal at C. So if I'm looking at the n prime is to the right, or putting it into compression, and n double prime is the same. So n prime plus n double prime is equal to 7.82, and that's to the right or compression. Good. And that are, when we get to those two members, when we're doing the shear force and bending moment diagram for those two members, though, or the axial force diagram, if we were going to do that, we would use those local coordinates for generating that. So that's exactly what we're going to do now. We're going to do the shear force and bending moment diagrams. So I'm going to scroll down my page one more time, draw out my diagram so I can add to it, and do our shear force and bending moment diagrams. Okay, so we need to look at our free body diagrams. I can't fit everything onto the page, which is unfortunate, but obviously you're taking the information that you have in your free body diagram and you're bringing it down and drawing it onto shear force bending moment diagram. So the first thing, in this context, we have to adopt a sign convention. And so for us, what we're going to do is we're going to adopt a sign convention as if we're looking from the inside at the bottom of the beam. It doesn't matter whether we're looking to the left or to the right, we're going to be looking at the bottom of the beam. And so if I were to look at, say, that first member, or on the second member is easier, I'll just draw in my differential element. Remember, our sign convention we've been using for shear force bending moment diagram is here. So that's going to give us our sign. And all of those would be positive. So our reference is us looking out using that sign convention as positive. So I'm going to grab my pen, grab my ruler, work my way around the shear force diagram. So to start off at A, we have our reaction 21.09, pushing us up into positive territory up to 21.09. And we know that we arrive at the far end at a value of 3.91 going up, going up or away to the left. It gets a little bit confusing in global coordinates, 3.91 going to the left. And so that's going to be a negative shear for us. And so we can draw in our shear force diagram. Remember, it is linear. And that gets us to negative 3.91. It's linear because of the uniformly distributed load of 5 kilonewton per meter acting on. And then I'm just going to very quickly use similar triangles to compare the total change 25 and figure out what this distance is here. And that distance is equal to 0.78 meters. So we're going to keep working away around the thing. So we're at member BC. So this is where we have to look at the normal and the shear force values in local coordinates, because we need the normal or the parallel to the cross section. And so what we have here is in shear at B, we have 8.6 down, which would be negative for us, right? Now we're on the negative face, it's going down. So that's a negative of 8.6. So I'll just draw that down, negative 8.6. We have no forces applied across the length. And so that takes us across, and then we go back up. So that's negative 8.6. You can put a negative in there. So that's a positive, that's a negative. And then again, we have to use the local coordinates when we're looking at C and D. So if I were to look at C, we said shear was 3.90. That's going up. So that should be positive for us. So I can, sorry, jumping around here. Sorry about that. 3.90. and there are no forces applied, so it stays constant over its length, and that's positive. And we got a minor truncation error here, so we have 3.91. Positive right. And that comes down and disappears and brings us to the left. So that's our shear force diagram. And if you were asked to identify where and what the value of the max shear is, of course, we have the max shear occurring at A of 21.09. So moving on to do the bending moment diagram. So the first one that has an interesting shape, of course, is the first one. We have no moment at A, so it's equal to a value of 0. We know it has a positive value of 42.95 at B, so I can draw those in. And we can see that, so we're going to be having a positive slope moving up from A, and it's going to reach a point of inflection and maximum at 0.78 meters down from B, so at about there. So if I were to draw this in, it would do something like that. And we would have to calculate what that value is. Again, we already know the distance. We calculated it when we did our shear force diagram. That distance is 0.78. And the easiest thing for us to do is to take the area of the triangle, 1 half, 21.09, times the distance from A to that point, and calculate that out. And we can figure out that this value is 44.49. And let's write in this 42.95 here. So we can transfer that 42.95 up here. And it reduces down to 0 at the far end. Starts at 0 and goes up to a value of 19.55 at the far end. Starts at 19.55 positive at that end and reduces down to a value of 0 when we get back to the support at E. And so again, looking at that, if we had to identify the point of maximum moment, clearly it's going to be the 44.49, and the location will be 0.78 meters down from B where it occurs. And that is the problem. I'm just going to scroll up here because we've covered a lot of territory to get down there. It's actually a fairly straightforward process, but hard for me to display on a single sheet. So really, I would say the errors that happen here tend to be mathematical, going through sign conventions, how they're applied, or some people struggle with that transition from global coordinates to local coordinates. Certainly, I prefer to keep everything in global coordinates all the way through the frame and only look at local coordinates when it comes time to prepare to do the shear force bending moment diagram. I find that that works out better for me. So hopefully that's useful to you. Certainly how to apply the hinge, using some of the moments about 0 equal, or some of the moments at the hinge to be equal to 0, and a partial free body diagram with the method of sections to resolve your reactions, and then going on to look at each of the members. So hopefully that was useful to you, and look forward to seeing you in the next one.